Hello. So I want to start adding some general transformations to my objects. Or really what I want to do is make a full scene which is unrestricted. It has a whole bunch of different models. And as part of that, we might want to be reusing the same model. So we don't want to have to load in the same model multiple times. That's pretty wasteful. So anyway, imagine we have our model, our statue, and the statue is spinning, let's say. Doesn't matter which way. And here the statue is here. Now its head is facing more towards the camera. And we have, oh, come on here. We have a ray which is shooting, I don't know, shooting towards the head. Now, the question is, how do we calculate this? We definitely don't want to transform every single vertex on the model. It could be quite big. So we have this concept of two different coordinate systems. We have object space and world space. Now in world space, we have this sort of scenario. The head is facing towards us and we are looking directly at the head. But in object space, if we were to take that backwards, it's as if the model never changed and the ray is now just coming from the top down. So world space is seeing things from our point of view and object space is seeing things from the object's point of view. Now the benefit of this is that we don't need to transform the object, we just need to transform the ray. So let's go to world space. And in world space, we have that the position we hit is given by the ray's origin plus the parameter t times the ray's direction. So let's say we have a model transform. The operation which takes the object and puts into world space is the model transform. I'll call that t. And if I want to go backwards, we would apply the inverse of the model transform. So we're just going to completely forget about t, and from now on we're always going to talk about the inverse, t inverse. So imagine transforming everything. So let's say we hit here at some point p, and we hit here at some point p dash. That's just some sort of transformation. We transform everything in the ray. So p dash is the inverse of the inverse of the model transform applied to the original point p. But the original point p is this vector equation. So imagine we have the inverse and we're applying it to the origin plus t times the direction. Now, the matrix multiplication is a linear operator, which means that, let's say A is a matrix, and we have the vector inputs u plus v. That is the same as transforming u, transforming v separately, and adding them together. That's the property of a linear operator. So like I said, T inverse is a matrix, so it is a linear operator. Whoops, come on. No, don't do that. Okay, so we apply so we invert the direction, the origin, and we invert this t times direction. But then furthermore, another property of a linear operator is that scalar multiplication can be pulled out. So note that, d is a three-dimensional vector, whereas t is just a real number. So a property here is that if I have some scalar multiplier times the vector v, that scalar can just pull out the front. So really our position is given by t times Oops, that should be an inverse there. Now, I don't know if I'm selling this hard enough, but this is actually a really profound result. This is actually super cool. So I'll hash back over it. Here we have that our position is equal to the inverse inverted origin plus t times the inverted direction. And then up above, we have that our position in world space is the origin plus t times the direction. But note that the parameter t is exactly the same. So what this means is that ray tracing to an object which has a general transform applied to it is actually very straightforward. All we need to do is transform our ray by the inverse transform, do our ray tracing, and then the t value that we get there will apply in world space as well. So that is super important. We'll have a look at that. But I just want to make one more note. So far it's all been about the inverse transform. But what we might also want to do is we might have a normal vector, some information, like this little surface has a normal, and we want to know what is that in world space. So how do we map the normal into world space? You could be saying, okay, no problem. Well, we have a transform t, we'll just apply t to the object space normal, but it would be better if we could save a bit of space and just talk about the t inverse. So the idea is, let me write this. I'll write the normal in world space is, let's go with this, t times the normal in object space. But let's not do t. So let's say t inverse times the normal in world space is t inverse times t. Well, that is the identity, so that doesn't matter, that's fine. Okay, so then I want to work with this. So if I multiply everything by the inverse of the inverse, then that will be the identity. And don't worry, this isn't some perverse little exercise that I'm doing. There is a point to this. So the point is, if we invert the inverse, that's what we're after. But inverting the inverse is a horrible calculation. It's bad. But we don't have a general matrix. We don't have a general matrix. We actually have something which the fourth column is describing, let's say some sort of translation. Okay, so I'll just rub that out. So we have some translation in the X, some translation in the Y, translation in the Z, and then some sort of 3x3. Okay. And I'm going to make an assumption. I'm going to assume that my model transform does not have any non-uniform scaling. And so I'm going to assume, because this top 3x3, mostly for a geometric matrix, will either represent rotation or scaling, maybe some skew, who knows, but usually just one of those. So if I don't have any scaling, then this is just a rotation matrix. And I can enforce that on my side by not sending any scaling transforms. So if this is just a rotation matrix, then it's an orthogonal matrix, which means, let me just write T 3x3. That's the upper 3x3 matrix. An orthogonal matrix has the property that its inverse is the same thing as its transpose. So what I can do is, instead of writing all of this nasty stuff, I'll just take the inverse matrix, transpose it, multiply in world space, and somehow I'll need to cast that into a 3x3 matrix. And probably the easiest way to do that is to take the normal in object space, insert an extra 0, and then it works the same way. But anyway, so that's been a little long-winded, but I do think it's important to look at the concepts. So I'll step back over that. What we do is we transform our ray back from world space into object space by applying the inverse transform, which is data that we'll send into the scene. We will solve for t, and then the same t, we can put it back into the original ray to get the position that we hit. And furthermore, if we want to transform anything in our model from object space back into world space, then all we need to do is multiply pretty much by the transpose of the inverse, at least for a direction vector. Anyway, so hopefully that was interesting. Let's get into the actual code. Okay, so I'll just fire this up. Now, if you go into the GitHub repo and head to the start folder for this exercise, for this session, you can find pretty much what I've got here. But just the same as the past videos, I've added some to-do items, and you're welcome to pause the video at any time if you want to jump in and do some stuff. Okay, so I'm going to start with the shader, and then, well, let's see, we have a scene, and a scene has a model has triangles, so I'm going to try from the triangles, and then I'll go from the base level objects back up. But anyway, to start with the shader, so it says here we need to add a normal for each corner. So see that I have corner A, B, and C. We can just copy this and declare that we are going to have a normal. And I'm going to put it corner first and then normal, corner first and then normal. Just like that. And I'm just explicitly stating that there's some implicit padding, so when I send the data over, I'll need to be aware of that. But anyway, that's fine. I've got the triangle. The sphere is fine. Object data. All of this is all okay. Now here, to do, add an inverse model transform for the model. Okay, so because we're just rendering one model in total, it makes sense to just have a global object that we'll send in. So I'll say, I'm going to call this inverse model. That will be a mat 4x4 with float 32 components. Okay, so we have render state, that's all fine. This main function, we don't need to change that. Now, ray color. So as we can see here, I'm making a copy of the ray, and that's okay. What I'm going to do is I'm going to call this world ray, because it's the ray in world space. Okay, and then at the same time, I'm going to make an object space version of the ray. So I'm going to call this object ray. Now, I want to transform everything. So I'll take the scenes inverse transform, and I'll multiply it by the ray origin. But the scene inverse transform is a 4x4 matrix, so we'll need to construct a vec4. And what I'll do is I will, because I want to also apply translation, I'll add 1 as the 4th component. Then what I'll do is I'll get the XYZ components, so I'll get a vec3 out of that. Does that make sense? So I transform the origin according to the inverse transform. I add on that 1.0 on the end because I want to include translation transforms as well. And then I get a vec3 out of that. Okay, now I'll do pretty similar here. So I'll take the scenes inverse transform. If I can spell inverse. It was inverse model, wasn't it? Let me just double check. Yes, inverse model. Okay. Okay, and unlike with the ray origin, if I translate the direction will be unchanged. So I don't want translation to have any effect, and to ensure that, I pass in 0 as the W component. Okay, cool. So I loop through, I do all my bounces, and I will alter this, but for now I'll keep it the same because it's a cool sort of effect when it doesn't quite work. So what we do down here is we want to set up for the next ray. And oh, by the way, when I go to trace, I'm going to pass in the object ray. So nothing else needs to change on the ray tracing side. We just transform the ray appropriately and then send it in. But when we set up for the next trace, that needs to be based on all of the world space coordinates and things. So what I'll do is I'll actually calculate this. So we'll go So I'm not relying on the position, which I wrote in the shader, because that was based on the object space ray. But we know that the t value from the render state is valid in all spaces. So we can use that to reconstruct the origin. And what I want to do is reflect the world ray direction around the normal. Yep, the normal is being set up correctly. Okay, cool. So that is setting the position in world space, and then we can take that and use the world space info to reorient the object ray. Okay, so that should be fine. Fingers crossed. So let's close that for now, and I'll just go to trace. This is probably fine. Now, just a note on the stack. So at the moment, I've got 15 elements in my stack. The stack tends to grow with the log base 2 of the number of triangles. Off the top of my head, I had about 31,000 triangles in that model, and I quickly calculated 2 to the 15 is about 32,000. So we're good, we're fine. But in future, if we trace even larger scenes, we might want to increase this number. For instance, a size of 20 will cover us to about just over 1 million triangles, but I'll keep it at 15 for now. No more than we need. Okay, so I go ahead and, well, we don't need this one. That's fine. Now this to-do is dodgy. I was up till 1 AM debugging this, and I think it's better not to do that one. Okay, because we're already setting up the object space in the ray color function above. That's what it was. Okay, just quickly checking through here. Okay, right. So now we need to work out the normal. So by the way, I mean, it's not a big deal, but we probably don't need this parameter anymore. Okay, so. Use a convex interpolation in barycentric coordinates to get the normal. Okay, so remember that barycentric coordinates are u, v, and w, being the three corners of the triangle. And because they all sum up to 1, then we can replace 1 minus u minus v for w. So what I'll do is I'll say, okay, I'll get my normal. That's a vec3 32-bit floats. So I'll just write this. It'll be w times the normal at position A. Yeah, and v times normal C. But because of that trick, for w is equal to 1 minus u minus v. Okay, so there we have it. Then the next step is I need to transform that into world space. So what I'll do is, let's go transpose the inverse model. So just like I was saying before, this will really be the same as inverting it for the rotation component. And then we'll go take the normal, add 0 as the fourth component. So transform that and then get the 3 components, and then just for safety, we'll then normalize that. So there we go. Okay, so long story short, we trace, we get the normals at each of the coordinates, we interpolate between them, and then send that back into world space so that we can reflect around it properly. Geez, this triangle function's getting pretty big. Oh well, as long as it works, right? Okay, now, the axis-aligned bounding box, no worries, because we have already transformed the ray into object space. So if we want to transform all of the acceleration structure, it's fine just to use the same trick as with the triangles, because the acceleration structure will have the same model transform applied to it as all of the triangles in the object. Okay, so I think that's okay. And like I said, I'll come back to this, but it is fine for now. Now let's go to the triangle and see if there's anything we need to do here. Yes, there is. Okay, so we need to get the normals at each corner. And then we need to initialize the normals list. No worries, just the same as the corners. We'll go this normals. And then, yeah, so what we'll be doing when we load the model is setting each of the corners by hand. However, it would be nice if we adapt this build from center and offsets so that it also, what am I thinking? So that it also sets a sensible value. So just under, okay, so just under this loop, we have now set each of the corners to some position. What I'll do is I'll get 2 edges. Okay, great. And then we'll do the same thing again to get the direction vector from corner A to corner C. And then we'll calculate the normal based on those edges. And then, yeah, I know it's a little weird, but we'll push that same normal for all three corners. So if we use this function to produce just a random triangle, then the face will be set accurately and it'll be a flat face. So all three corners will have the same face. Okay, cool. I think, yeah, that's it. So no worries. Triangle is done. Now the next step back from the triangle is the object model, because the object mesh, because it's loading a whole bunch of triangles. Okay, so add an inverse transform matrix. Okay, so I just hit tab to import that. Yep, okay. Right, so now we need to, for our constructor, when we say, hey, I want to make an object mesh, we're going to also specify, and I want it to be here. So I'll have a position and a set of Eulers. And what was I thinking? I also need to store those two. Okay, excellent. So what am I doing? So we're taking in the position and Euler in the constructor, and then we need to take that information and use it somehow to, make the inverse transform. So first of all, we'll just store that data. And then we'll make a blank matrix ready to fill. And then what I'm going to do, so if we look down below, on construction, we want to set up the inverse model transform, but also I'm going to make an update function so that the model changes its transform. So it seems like I want to make a single function that can be called from both. So I'll call this, calculate transform. And I'll work on that down below. Okay, so I'll just stack a bunch of these transformations together. So I'll say, okay, let's make a blank model matrix. And then we'll stack on a rotation, maybe rotate around the z-axis. Now, this is where things get a little weird. So I'm going to put it into model. And then I'm going to stack that. Does that make sense? We're going to stack it into model and then store the final result in model. But then we need an angle, and that angle needs to be in radians. So I realized for whatever reason, I just don't have a conversion function. So let's make one of those. I'll just make a new file. I'll call it math.ts, and I'll export a function, which I'll just call the standard degrees to radians. That takes in some angle, and it will return. And I just noticed there's another class which uses this, which is the reason that I'm putting it out into its own thing. But if we look down here in the camera function, we've got something like that. But actually, it turns out this is, why did I write this? This is inaccurate. It should be multiply by pi and then divide by 180, not the other way around. Okay, cool. So while I'm at it, I'll just fix up the camera class as well. So for the camera class, I'll just say, alrighty, import degrees to radians, and then we can call that function down here when we're getting the forward. So this is really degrees to radians, this theta. Okay, and over here, this will be okay, that's fine. So then we can go back and then we can import that converter. And use it down here. So that was the Z component of the Eulers. Okay, excellent. So that's the rotation around the Z. I'm also going to, I mean, we could put in all of these, but I'm just going to do rotation around the X. So then we'll go ahead and invert that. We'll store it into our inverse model variable. It will be the inversion of that model matrix. Okay, excellent. So what this function does is it looks at the position in Eulers, calculates an appropriate transform, and then stores the inverse of the transform. Okay, so I'm happy with that one. The next item on our to-do list is to make an update function which spins the model around the z-axis. No worries. So I'll just say, okay, update. Now I want this to be frame rate independent. I want to access Eulers around the z-axis. To make it frame rate independent, I'm going to take some rate, which is a number representing sort of a correction factor. So if the rate is smaller, then we're going at a higher frame rate, and if it's higher, then we're going at a lower frame rate, if that makes sense. So if we're going at a higher frame rate, we want a lower number because we're going to, hopefully that makes sense. Maybe I'm over explaining it, but then I just want to do a modulus test. So if Eulers, and of course, after we do all of that, we want to calculate our transform. Okay. Yeah. I mean, there we go. It's very, getting a little stuck into it, but it's very cool. Okay, so we have initialized. That is fine. This is all fine. Vertex data, no problem. Text coord, no problem, no problem. Right. So if we have a look before, here we're setting the corners of this given triangle. But this function here, read corner, can access the position, texture, and normal. So what I'm going to do is I am going to modify this function so that it takes a reference to the triangle that I'm talking to. And then what that function does is it works with the triangle and sets everything that it needs to. So I'll just say, all right, we have a triangle. So does that make sense? What we're doing is we are basically taking the triangle that we want to work with, and we're just modifying the triangle directly with the information that we have available in this corner function. Cool. So the triangles should now be set up properly. Maybe the scene, because the scene deals with And triangles. Right, okay. Right, so when I make the object mesh, I need to also specify its position. Let's just keep everything zeroed out for now. So position is at the origin and Euler's just no modification. And we probably don't need to create the same thing twice. Whoops, that's okay. Yep, set it up, okay. And this is something I forgot to remove last time. I've already done that down below. Okay. Right, so now we want to take an update function. It needs to tell the statue to spin. So all we really need to do is just make a function called update. And I'm going to take in the frame time and work with that. And I'll tell the statue to update. And I want to take, for the rate, the frame time as a proportion over 16 frames per second, which is about 16 2/3 milliseconds. Okay, so I think the rest of this is fine. I'll just close this down. Yeah, this is all fine. Okay, so onto the renderer. We have a few things we need to do because the renderer is in charge of sending data to the shader. Alrighty, so yeah, the model is pretty big. So I'm going to use a variable to keep track of whether we need to upload new data. I'll just call this loaded, and that will be a Boolean. Yeah, loaded to false. Okay. Need to change things. Okay, so parameter buffer needs to include that 4x4 matrix. So a 4x4 is 16 floats. 16 times 4 is 64. So we have another 64 bytes worth of data. So now the buffer size is 128 bytes. That's fine. And now for these ones, okay, I'm including 3 vec4s. We're going to have to allocate that much space, including padding. So 3 vec4s is 12 floats, which is 48 bytes. 64 plus 48 is 112. So now every entry for a triangle will take up 112 bytes. And the rest of this is fine. Yeah. Okay. Make bind groups, that's okay. Make pipelines, that's okay. Prepare scene. Right, okay. So I'm just going to add an inverse model transform here. Okay, that's fine. So we've got it there. Now, if you look down below, we're doing a buffer write operation, which is sending in a whole bunch of, floats and things. But we've got a 4x4 matrix. That's a bit much to write all in one go in this sort of, does that make sense? This sort of unpacked format. So what I'm going to do is I'm going to perform a separate write operation. So we'll say, okay, get the device queue and use the write buffer. Now the buffer we're writing to is the scene parameters. Then the offset is 64 bytes because 64 bytes have already been written to this buffer. The data will be, we go scene data inverse model. Now it might complain about this. Let's leave it there actually. No, that's it. That's it. So we'll complain about this. All we need to do is specify that this is array buffer. And thank you, autocomplete. That's really helpful. There we go. Okay. So we're just, we write the first few bits by hand, and then we write the whole matrix in one go. Okay, cool. So to do, only send the data if we need to. So what I want to do, now what I could do is I could do something like if not this loaded, then do all this other stuff. But excessive nesting is bad, so it's better to test for early exit than continuation. So what I'll do instead is I'll say, okay, if we've already loaded, then just cap it here. Okay, but if we get to this point, we'll just specify this variable so we're not loading it in future. Okay, update the size of the triangle data. Right, so here I've got 16 floats, but now I'm writing in another 12 floats for the 3 vec4s. So that'll be 28. Now this will just be a little bit of a nightmare, but that's fine. Alrighty, so where are we? So we've got so going through for each of the 3 corners, and I'm going to unroll this middle loop. So what I'll do is I'll just do this for corner A, and then I'll generalize it. So let's go to stride of 28. Yep, and then 28 plus 1. This is a lot of fun. 28 plus 2, what am I going to do? Right, so, and I don't know, 28 plus 3, whoopee. Oh, so we've got the padding there. Right, so we write the corner for position A, basically, and then we want to write the normal data for position A. Okay, so write each of the corners, and then the offsets are 5, 6, and then that padding there. Excellent. So then the question is, how do we generalize this? Well, when I go to the next corner, I'll be continuing at 8, 9, 10, 11. And so we can say that the stride added by stepping to the next corner is 8 floats. So then I can just go ahead and add that in everywhere. Okay, it's looking good. And then just for formatting purposes, tab it over. Okay, excellent. So that has set all of the corners and normals. Then down below, we're looking at the writing in the RGB data for the color. So of course, our stride is 28. And then we're saying, okay, well, what's the offset? Well, once we've written 3 corners, we've written 3 lots of 8 floats, and 3 times 8 is 24. So if you think about this, we're writing in the color at position offset 24, 25, 26, and then the last one will be offset 27. Hopefully that makes sense. Maybe I'm just like spending too much time explaining a basic concept, but I mean, it is good to see it every now and then. Okay, so then down below we write everything and we say, well, how much data do we write? Well, we write 28 times the number of triangles, because each triangle we're writing 28 floats into the shader. Then none of this needs to change. This stuff here should be fine. Fingers crossed. Hey, who knows? Wouldn't be the first time I've surprised myself. Okay, yeah, so like I'm saying here, this is a little dodgy, but for now, because I don't want to do a full refactor just yet, we'll go signal for the scene to update itself. And luckily we have saved our frame time as a variable, so we can just pass that in there. All right. Fingers crossed. Let's see how this is going. We'll just open up a terminal and hit npm start. Open that up in Chrome Canary. And it's not, oh, nice. Okay, it's not working. Let's find out. Inspect, what is it saying? Okay, line 124. Let's find out. Oh, right, okay, yeah. So I want to set the direction for the world ray. Okay, so I'll just reload that. By the way, let me know, do you like this more interactive style? It feels, somehow it feels more chilled to me. So we can see something bad is happening. Okay. So that's not meant to be happening. Why is the sky spinning? Well, remember that what we're doing is we're sending this ray out and we're transforming it according to the model. And then, does this make sense? Yeah, so the ray color, oh, that's fine. No, the trace is taking in a transformed ray, and that is testing things. So if we go right down to the bottom, it's this problem here. We're sending in the ray direction, but which ray direction? The ray which got spun according to the model. So no problem. What we can do is we can just take all of that, take it outside, go back to the function that called it, because we need to sample the sky according to the world ray, not the object ray. So I'll just go maybe back up here, and I'll just get rid of this, and we'll handle that up here. So if we shot it out and we just didn't hit anything, then at that point we'll sample the sky. So we'll say, maybe just do it like this. So we'll say color equals color times this thing, and that will be based on the world ray. And then after that point, we'll then break. Let's try that. Oh. Oh. What's wrong? I wasn't expecting that. Okay. Oh, something obvious, of course. Okay. You see, the more I get into this stuff, the more I realize that, like, staying up till 3 a.m. debugging something isn't necessarily a flex, because half the mistakes are things like that. I think the flex is that you don't make those mistakes. Okay, cool. So as you can see, the model is spinning around its z-axis. Now, when we loaded this the first time, it did look like this. So let's apply a rotation in the x-axis just to orient it right way up. So we'll just go to the scene, and here where we make scene, maybe above that. Okay, let me put in a rotation of 90 degrees in the x-axis, see what that looks like. Okay, oh god, god, oh. I don't want to get demonetized. Okay, so that was almost correct. Now let's rotate it by 180. I say demonetized, I make like $1 a day. This is really not a flex. Okay, cool. All right, so as you can see, we can now load in an object and orient it however we wish. So This has really been an example of what's called a bottom level acceleration structure. It's an acceleration structure which just deals with the base triangles of a model. What I want to do in the next video is construct a top level acceleration structure so that basically I can plop in a bunch of these at different positions and orientations and still have an acceleration structure to let me trace down to those core triangles, if that makes sense. I am glad to say that the performance is pretty decent. I mean, like 6, 7, maybe up to 10 milliseconds. I'm perfectly happy with that. So yeah, I mean, maybe in future I'll look at different acceleration structures and techniques and things, but I'm pretty happy with this for now. So thank you if you made it this far, and and if you skipped right to the end, that's okay. No worries, I appreciate you. And yeah, all the best, and I'll see you again next time. Bye.